Alright, so this is the first tutorial that you're going to have that we have not done yet. New concept called the derivative, which way back in the day started with what's called the tangent line problem. If you've been in physics, then you know who Isaac Newton is, and he helped solve a lot of these problems along with Gottfried Leibniz. And he's one of my favorites. He just had a better attitude than Newton. But anyways, alright. So let's take a look at these three pictures below. These are just three random different functions with curves. And on all of these curves is a point called P. So the first thing that we have to do is understand what a tangent line means. And when we deal with certain things, finding tangents are very easy because they have an exact definition. But with curves, there's a pretty big problem, and you're going to see why. So let's first of all define tangent. It is a line that represents the slope at point P. So it's hard to determine exactly what a slope at any particular point would be because we know from algebra that there's something called a slope formula. And if you don't remember, this is what it looks like. And just by looking at this, it's easy to see why finding the slope at one particular point would be really difficult. Because when I look into this function, y2 and x2 represent 1 point, and y1 and x1 represent 1 point. So it's almost as if I need two different points to determine the slope. So how do I know the slope at 1 point? Now you can see the problem. This is what they studied for a very, very long time. So I'm just going to sketch out some ways in which we can determine the slope. So if you look at the very first picture at the bottom, another way to help determine this tangent line is by using what's called a secant line. And a secant line is very simple. It uses point P, it uses the point that you're using, or wanting the slope at, and then another point just somewhere nearby. So I could pick this point right here, and you can label anything you want. I'll label it E because it's my first initial. And what this does is it connects those 2 points with a line. And what that should do is estimate the slope at point P. And if you can think about this a little bit more, if I were to make E get closer and closer and closer and closer to point P, the more approximate and the more accurate my slope estimation is going to be, which is a concept of limits. Let's take a look at the next picture. So the problem is I could choose this point all the way over here. I'll choose my middle initial M. And when I connect those 2 points with a secant line, it looks like this. And just using our common knowledge, that slope does not look anything like what we would expect it to be if it were really at point P. So as I approach P from this direction, from the left-hand side, my slope would be better and better and better. All right, and the last picture. So let's say point L for my last name, is all the way down here, and I were to connect it with point P, and that's a pretty steep slope. That would probably give a pretty accurate slope estimation, but we want to, once again, get as close as to P as we possibly can. So that's the concept of this tangent line problem. And the slope formula plays a very, very big part in all of this. In fact, the concept of derivative comes from this. You thought it was very basic. Well, watch what happens to it. It gets pretty cool. All right, so let's take a look at this tangent problem another way using a different graph. Okay, so we're going to look at this a little bit more in depth and use some more accurate notation. Now, P, as far as this graph or any graph is concerned, can be at any arbitrary point we want as long as it's on the function. So we're going to represent P like this. My x coordinate is going to be represented with the c, and then the y would just be f of c. And this is what we're going to use in our picture. So when I take a look at this function, I'm trying to get this point that's right here above p closer and closer and closer to p until I get the best, most accurate slope that I possibly can. Now, we do know a couple things, and keep that slope formula in mind. I'm going to rewrite it right over here for you, just in case. All right, there we go. So let's take a look at a couple things, because I want to see what this looks like in terms of any arbitrary point. So you see here that this numerator, this y2 minus y1, very simply just represents a change in y. So the denominator would be a change in x. So when I look at my picture, I'm going to create my rise over run. Oh, that does not look anything like a rise over run. Sorry about that. Forget that I did that. Let's start here. Okay, here we go. All right. So this would be my run, and then this would be the rise. Okay. Now, this change in x, I'm going to represent by delta x, and that could represent any distance from this point P to any other arbitrary point I'm trying to get it close to. And the same thing goes for the change in y. That's going to vary based upon how close this other point is getting to P. And this point P, we already said, was the same exact thing as C, and then f of c. That's how we are portraying any arbitrary point. Let me rewrite this so it's a little bit cleaner. F of c. It won't do it. There we go. All right. It's a little sloppy, but you understand what I mean. All right. And then, of course, this point up here is going to be the tricky one, because how do I represent this point? Well, I definitely know that the minimum x value, okay, which would be right here, that's where C is right now, I would add this distance here to get to this red point. So in other words, that could be represented as C plus delta x, whatever that might be. And my y value, which would start here at some y value here, which is f of c, okay, would be subtracted from this value up here. So this could be represented another way by taking this and just plugging it in to my function. So I could say this distance, this y distance, is the same thing as if I took my x value, which is c plus delta x, and plugged it into my function. So I could say f of c, the c's don't work, plus delta x. Okay. And it's okay if you didn't grab that all the way, but all I have to do with this, if this was a real x value, some number, all I would do is plug it into my f of x function and I'd have my answer for y. So that's all we did, and it comes from this business over here. Okay, now why is all of this important and why do we even care? Well, going back to our limits, I'm going to write at the very bottom here a little bit about them, and we're going to see what's called the derivative start showing up. So I'm trying to find a limit to where this delta x business is getting closer and closer to 0. In other words, I want this piece right here in my graph to be as small as possible to p, within a 100 millionth of a unit, okay, something ridiculously close. And it is using the slope function in that I'm trying to find the change of y over the change of x, and I want this change of x to be as small as possible. Now, using our new coordinates and the way that they're being represented, I could very easily write this as the limit as the change of x approaches 0 of f of c plus delta x, because that represents my y2. Okay, that guy's right here, y2. And I'm going to subtract y1, which was this guy right here, f of c. And that's going to all be over delta x, and that is just as delta x. So that one's pretty easy. And this is all equal to m. Remember that the tangent line problem is that I want to find this line that has this particular slope. Well, this is all about slope. You're just seeing it in a completely different way. My numerator describes the change in y, and my denominator represents a change in x. So that describes the tangent line problem. The next tutorial will be using this definition, this limit as change of x approaches 0, in an actual problem.